In this lecture, we're going to start our last big topic for the term, which is the Ising model. This is another model where we're now dealing with interactions rather than just the non-interacting systems that we've looked at for most of the term. In this lecture, we'll sort of introduce the model and get a feel for what analytic techniques we have available to try to get an understanding of it. And in Monday's lecture next week, we will look at numerical methods, which you won't have to reproduce at all, but just I wanted you to get some idea of how things work when you're dealing with large interacting systems. And then just to sort of round things out, Wednesday next week, we'll have a lecture on applications of statistical mechanics outside of physics. And actually, several of these are going to connect to the Ising model. So it's this is also a good lead in to the last lecture. The Ising model is a model of interacting spins on a lattice. Okay. So the simplest case would be a one-dimensional lattice, which is to say just a string of points. Okay. So we'll identify our lattice sites, number 1, 2, 3, 4. Okay. And on each point of the lattice, we have a spin that can either point up or down. Those are the only two options. Okay. So this is a simplified model. It was first invented to try to understand ferromagnetism, which is to say, if I have a piece of iron, iron's a bad example because it's an extremely strong ferromagnet. I have a piece of nickel or cobalt, something that's ferromagnetic, at a sufficiently high temperature, then it will not be magnetized. Okay. But if I slowly lower the temperature, I arrive at a temperature called the Curie temperature, where the material spontaneously magnetizes. And we don't know what direction that magnetization is going to point unless there happens to be an external field applied, which makes it prefer a particular direction. So if I've got a vertical magnetic field and I cool my material down past the Curie temperature, when it spontaneously magnetizes, it'll preferentially magnetize in the vertical direction, pointing along the magnetic field. This is how permanent magnets are made. You take some ferromagnetic material, you apply a strong enough field that when it magnetizes, it aligns the domains, and then you have this permanent magnet. Okay, so now I just used the word domains. What do I mean by that? It turns out for something like iron, the phase transition happens sort of locally. So if you look inside, if you could look at the magnetic structure of a piece of iron, you'd see little domains. So here's a little domain and it's magnetized in this direction. Here's another domain next to it and it's magnetized in this direction. Right? And another domain here, maybe it's magnetized. So it's like locally the thing makes a decision, says, hey, all of the spins want to point in the same direction energetically, or in terms of free energy, that's what's favored. But it's very hard for spins at one end of a chunk of stuff to communicate with spins at the other end of a chunk of stuff. And so you get this local order. But if you don't have a global external magnetic field applied, that local order doesn't get to graduate to global order. Okay. But either way, this formation of domains, either aligned with each other or not, is this transition that was sort of the original reason for studying the Ising model. And as I mentioned at the beginning, it turns out the Ising model, you can use it so many places. We'll talk about a couple of them at least briefly in the last lecture. Things like neuroscience. Okay. Good. So this is our picture. We've got these spins. And now what do these spins do? Well, they're not moving around like a gas is, right? They're pinned to their positions. What these spins do is they interact with their nearest neighbor. Okay. So spin 1 and spin 2 are at lower energy if they're aligned with each other. It doesn't matter that they're spin up or spin down, right? So 1 and 2 both pointing up, 1 and 2 both pointing down. This has the same energy. So it's not the orientation in space, it's the orientation relative to one another. Okay. And so we'll refer to spin up as s equals 1 and spin down as s equals minus 1. And that gives us this interaction potential minus epsilon. Epsilon is just some energy scale associated with this coupling, right? Minus epsilon times S1, S2. That covers their interaction. Minus epsilon S2, S3. That covers their interaction. Minus epsilon S3, S4, their interaction, and so forth. So however long our chain is, our interaction potential will have one term for each nearest neighbor pair as you go down the chain. Okay. So simple case, just to get the ball rolling, if I have a chain that's only too long, we can just calculate the whole thing. Right? Both spins are up. That means our interaction is minus epsilon times plus 1 times plus 1 minus epsilon. One up and one down, minus epsilon times plus 1 for the spin up, minus 1 for the spin down, minus and minus, we get epsilon. Okay. Spin down, spin up, same story, minus epsilon times minus 1 times 1. So that doesn't matter the order, so this is also epsilon. And finally, as I promised a moment ago, both of them spin down means minus epsilon times minus 1 times minus 1. The minus is canceled. We end up with minus epsilon again. And as I said, the energy for both down is the same as the energy for both up. So I should say we're assuming here that there's no magnetic field that makes a difference between these two. Okay. So we would say, right, these are degenerate levels. You have two levels that are energy minus epsilon, two levels that are energy plus epsilon. If you apply a magnetic field, it will break the degeneracy between this state and this state, because these two both have a net magnetization, and so if they're parallel or anti-parallel to the field, that'll make a difference. This is something that you'll explore on the homework. But for the lecture, we're just going to talk about the interactions because that's sort of the new part, the more difficult part. Okay. So that's if we have a chain of two, and we want to write the partition function. I've got two states with energy minus epsilon. So 2e to the minus beta times minus epsilon just gives us beta epsilon. And then I've got two states, these two, with energy epsilon. So 2 times e to the minus beta epsilon. This hopefully looks familiar. We've seen hyperbolic functions earlier on in the course, right? E to a real power plus e to minus that real power. This is going to give us a cosh, hyperbolic cosecant, hyperbolic cosine, not cosecant, hyperbolic cosine. And of course, it's this plus this over 2 is the hyperbolic cosine. So we've got double that and then 2 in front of each. So actually doubled again. So this is 4 times the hyperbolic cos. Okay. Good. So we've got 4 cosh beta epsilon. That's our partition function if we have a 2-element chain. If we have a 3-element chain, I'm not going to draw all the little dots and lines and so forth, but we can just represent this in terms of the spin configuration, right? All the spins up. This is going to have, we've got 2 terms now in our interaction potential. So we've got minus epsilon times 1 times 1. That gives us a minus epsilon. Plus minus epsilon times 1 times 1 gives us another minus epsilon. So we've got minus 2 epsilon. So I've got the full accounting of the 3-spin system here, and I'd encourage you to just pause the video, make sure you can work through and get the same answers here. Okay. And as an example, here we've got minus epsilon times 1 is minus epsilon, plus minus epsilon times 1 times minus 1, that's plus epsilon. So we had a minus epsilon plus a plus epsilon, that gives us 0. Okay. Good. If I take this whole thing, write it down as a partition function, right? I've again got 2 states that are now minus 2 epsilon. It's everyone up, everyone down. So that gives me 2e to the 2 beta epsilon. I've got 4 states that have 0 energy, so plus 4. E to the minus beta times 0 is 1. And then I've got 2 states that have energy 2 epsilon. These are the ones that have sort of the outer spins parallel and the inner one anti-parallel. So both interactions have a minus sign, which which is to say both interactions raise the energy. So 2 states, e to the minus 2 beta epsilon. Now I can pull out a 2, and I can factor what's left into e to the beta epsilon plus e to the minus beta epsilon squared. And again, this is 2 times the cosh, so we've got 2 outside, 2 cosh beta epsilon squared. Okay? And I could have rewritten this as 2 times 2 cosh beta epsilon. So you might look at that and say, seems like when we added an extra spin, we got an extra factor of 2 cosh beta epsilon in the partition function. You would be correct. We'll see how to solve this model exactly in the next section. But before we solve the one-dimensional model exactly, I just wanted to make a quick point about one dimension isn't the only dimension, right? We can have 2-dimensional model, 3-dimensional model. So as an example, I've drawn a 2-dimensional model and it's just got 4 spins in it, but we can have any dimension and sort of make here I've made a square lattice. We can have a cubic lattice in 3 dimensions and a hypercubic lattice in higher dimensions. The energy, the interaction potential, which in this case is the only energy, will be minus epsilon times the sum over nearest neighbors of SI times SJ. So in this case, I'm just going to go around the square. So first I have minus epsilon times 1 times 1, so that's minus epsilon. 2 to 3, I have minus epsilon again times 1 times 1, so I get another minus epsilon. 3 to 4, I get a plus and a minus, so this will end up plus epsilon. And then finally 4 to 1, again, I've got a minus and a plus, so this will be plus epsilon. So the total energy of this configuration is 0. So in some sense, the physics is the same in 1, 2, 3, 4 dimensions, right? We have the same interaction potential, and it's just a question of accounting for all of the neighbors. You get more neighbors as you go to higher dimensions, and it turns out that makes an important difference, which we'll see soon. But at least just in terms of writing down the energy, writing down the interaction potential, it looks the same. In any dimension, it has this form. We have 2 analytical handles for trying to understand the Ising model, this model of interacting spins. The first one is that in the 1D case, we can actually exactly solve the system. So we can calculate the partition function in closed form. And as you already know from this course, once you've got the partition function, you can find whatever else you're interested in, right? Take the log and get the free energy, take the derivative and get the average energy. If you've got the free energy, you can calculate so on and so forth, right? Good, so let's take a look at this. I'll also mention there is actually an exact solution for 2D as well. It is really intense. Who's not going to do that to you? The 1D solution I think has some nice aspects, and we can learn something from it. All right, so here we go. It looks bad down here. Don't worry, it's not as bad as it looks. So the energy, again, minus epsilon times the sum on neighbors, which in 1D is just the pairs sequentially as you go down your chain. So suppose we have n spins in our lattice. We'll sum over I from 1 to n minus 1 of s sub I times s sub I plus 1. This may look a little funny. Hey, we had n, why do we only sum up to n minus 1? Of course, it's because the last spin is this I plus 1, and this will actually be important to how we can do the exact solution. So the partition function is just the sum over every possible configuration of spins, right? Every single spin can be either plus or minus. Sum over all of these configurations, and the thing that you're summing between configurations is e to the beta epsilon times the sum of all the spin products. It sounds like quite a difficult thing to take a look at. Okay, there's a lot sort of being packed in there. So again, this notation, which is maybe a little unfortunate, is saying we're summing over every possible configuration, where configurations just mean for each spin you've picked either positive or negative. Now, this means that our number of configurations is going to be huge, right? So if we have n spins, for each spin we get to pick either spin up, spin down. We have 2 choices for each of n spins. So that means our number of configurations is going to be 2 to the n. Okay. So if we've got, well, you saw already up above, right? When we had 2, it was 2 to the 2. We had 4 configurations. When we added a third spin, now we've got 2 to the 3. We've got 8 configurations, right? This starts getting pretty intense if you have 50 configurations, right? You have 2 to the 50th. How big is that? I don't know. It's really big. 2 to the 10th is about 1,000. 2 to the 50th would be that raised to the 5th. So 1,000 to the 5th is 10 to the 15th. What is that? Billion is 9, trillion is 12, so a quadrillion. If you have 50 spins, you have about a quadrillion configurations. I probably undercounted a little. Maybe you've got 2 quadrillion. Anyway, it's more than you want to write down. It's also more than you can have your computer calculate, which will be important to our lecture on Monday. Okay. Once you try to do a system that's way too big for a computer to calculate, we need to, or at least to calculate directly, we need to come up with more creative methods. Right. But for now, we're going to hide all of that complexity in this notation. And since this is a bit opaque, let's make it a bit more explicit. So we're summing over S1 being plus or minus, S2 being plus or minus, right? Summing over each individual spin all the way out through Sn being either plus or minus. And what's the thing we're summing? Well, it's e to a big sum, which means we can factor it as a product. So e to the beta epsilon S1, S2, e to the beta epsilon S2, S3, and so forth all the way out. And now the sort of key observation is the spins at the 2 ends are only involved in one term of this product. Right? If I look at S2, it's both here and here, right? It gets to be Si and it gets to be Si plus 1 in different terms. So S2, that may be hard to work with right away, but S1, it's all by itself. It's only in one term. Or similarly, remember this only went to n minus 1 because S sub n only appears as an I plus 1. So this last term is the only place S sub n appears. So what do we do? Well, if S sub n is here and only here, then we can say we can do this sum, right? Doesn't matter what S sub n minus 1 is, there's going to be one term where S sub n and S sub n minus 1 are parallel, and one term where they're anti-parallel, right? If n minus 1 is spin up, well, we're going to sum over both configurations of Sn, up and down. If S sub n minus 1 is down, same story. We're going to sum over both configurations, up and down. And since the overall orientation in space isn't important, it's just the relative orientation, we can actually take this term out. When we do the n sum, we're going to get a term that looks like e to the beta epsilon plus e to the minus beta epsilon, right? Either they're parallel, in which case the energy is minus epsilon, and so this is e to the plus beta epsilon, or they're anti-parallel, in which case the energy is epsilon, and we get e to the minus beta epsilon. So this sum has given us what we've already seen a couple of times in this lecture. This is 2 times cosh of beta epsilon. So we've got our 2 cosh beta epsilon, and we've gotten rid of the sum over Sn. Now we're just summing out to Sn minus 1. But hey, look what happened. When we got rid of this term, S sub n minus 1 now only appears in a single term. Do the same thing, right? No matter what S sub n minus 2 points, S sub n minus 1 has 2 configurations, parallel and anti-parallel, right? Same story, run it. You just back up the video and run it again. So we can do the same thing to this term. Well, you can see the pattern, right? We can just do this until we're running out of spins, right? This term will get replaced by a 2 cosh beta epsilon. So we'll have 2 cosh beta epsilon squared, and we'll go out to Sn minus 2. Keep working our way back until we're down to just 2 spins left. Okay. When we have only 2 spins left, you can come back up here. We know what the partition function for 2 spins is, right? It's 2 times 2 cosh beta epsilon. So as we back up doing these sums until we've only got 2 spins left, we'll have n minus 2 copies of 2 cosh beta epsilon. And then we just, and this, right, I've written it on this side, but we could factor this out. We could pull this out in front of the sums because this doesn't depend on S1 or S2. So we've got 2 cosh beta epsilon to the n minus 2 multiplying the partition function for a 2-spin Ising chain. We already did that. We know it gives us an extra 2 cosh beta epsilon, so that becomes n minus 1. And there's just a spare 2 out front. Okay, so we've got 2 times 2 cosh beta epsilon to the n minus 1. This is the exact solution for the partition function of the Ising chain. And now the only approximation that we'd like to make, in truth, we're making this approximation because Schroeder makes this approximation. I think you guys can handle n minus 1, right? And a spare 2. But nonetheless, it's in keeping with the course, right? We've frequently said, hey, we got to n minus 1. That's basically n, right? We're working with large n, so n minus 1 and n are essentially the same thing. And so we can say, hey, we've got the 2 already. We're just down by 1 cosh beta epsilon. So we can say this is approximately 2 cosh beta epsilon raised to the n. So this is the in fact exact result. And this is the, oh, it's so close, and it looks a little nicer result. So we'll work with this one because it looks a little nicer. And I've realized I'm at the bottom of the screen. Sorry about that. I think my face wasn't in the way, but so here we are. Now, like I said, once you have the partition function, you can calculate whatever you like. So let's calculate the expected energy. It's a good thing to know about a system. So we're going to take this approximation, which is just for convenience. We could do it with the exact result. We'd get it. We'd actually get the same answer for the average energy. Okay, good. So let's do it. Well, no, we wouldn't. It'd be n minus 1 instead of n out front. As close as we wanted, it would be the average energy. Okay, so average energy. This is 1 over z dz d beta. Take our result here, right? Take the derivative with respect to beta. The n pops out front. This is raised to the n minus 1. And then we need to multiply by the derivative of the stuff inside. It's a derivative with respect to beta, so the epsilon pops out front. We've got 2 epsilon. Derivative of cosh is sinh beta epsilon. Remember, hyperbolic functions are actually slightly nicer than trig functions because you don't have to remember, oh, when do I pick up a minus sign when I'm taking derivatives? Derivative of cosh is sinh, derivative of sinh is cosh. Okay. And don't forget the 1 over z out front, or the minus sign. So minus, and z looks like so, shows up in the bottom. And now, this is why I said you'd get almost exactly the same average energy if you use the exact result, right? Because all of this stuff cancels. All that matters is that we have 1 extra cosh in the bottom and 1 sinh out to the side from taking the derivative of what's inside of here. So all of that cancels down to just a 2 cosh beta epsilon on the bottom. We've got a 2 sinh beta epsilon out to the side. The 2's cancel and give us a tanh beta epsilon, right? Hyperbolic tangent. And then we just need to clean up the constants that we sort of left littered around. There's the minus sign, there's the n, there's the epsilon. So our average energy is minus n epsilon, tanh beta epsilon. Easy. Why was I acting like interacting systems are hard? We can solve this one exactly. Okay. Like I said, in principle, you can't actually solve the 2D exactly. It's a bear. You don't want any part of it, at least not until you're in grad school. Maybe not even then. And beyond 2 dimensions, we can't solve this exactly anymore. And the Ising model is the simplest model of interacting spins. Okay? In particular, the fact that we've assumed they're either up or down simplifies dramatically compared to what I was talking about with the iron, where I said, oh yeah, magnetization can point this way or this way or this way or this way. if the spin direction is continuous, this is a harder problem. So we stick to the Ising model. All right, so here's our average energy as a function of temperature, or beta, right? So let's plot this thing. Of course, it's easier to plot versus beta because that's how it's written. The average energy is going to be negative. As beta goes to 0, the energy goes to 0, right? And as beta goes to infinity, tanh saturates to 1, right? Tanh has an asymptote at 1. If you think about it, it's hyperbolic sine over hyperbolic cosine. As you take x to be large, the e to the x part of the sinh, the e to the x part of the cosh, completely dominates the e to the minus x, and so that ratio becomes 1. So what we see is that the energy as a function of beta goes to 0 at 0 beta and asymptotes to minus n epsilon as beta goes to infinity. But of course, remember, the physical thing that you're more accustomed to thinking about is temperature. Beta is easier for calculations, temperature is easier for picturing, so beta going to infinity means t going to 0. As t goes to 0, we're going to get negative n epsilon for our energy. Now, what does that mean? Okay, let's think about this physically. The energy is due to the interactions, and in particular, if two spins are aligned, that reduces their energy by epsilon. If we're asymptoting to minus n times epsilon, that means every one of those interactions is reducing the energy by epsilon, which is to say the material is magnetized. So as we take beta to infinity, temperature goes to 0 and the material magnetizes. Now that's kind of like what I explained for the iron or some other ferromagnetic material, the difference being that ferromagnets have a phase transition at a non-zero temperature. And nothing sort of sharp is happening here. Okay? There isn't a place where there's a discontinuity in the energy or a discontinuity in the derivative of the energy, right? Tanh is an analytic function. We could take derivatives all day. This will stay continuous. So there is no phase transition in this system. And that's going to be important because in the next section, when we talk about our other analytic tool, it's going to be a way to find phase transitions, and it will erroneously tell us that there's a phase transition in 1D. So having the exact solution at hand is really nice here. We can just look. There's no discontinuity. There's no non-differentiable point and so forth. All the derivatives of the energy exist, so we're not looking at a phase transition. But we do magnetize gradually as we go to low temperature. So that's a rough plot of average energy versus beta. I've also made a rough plot of average energy versus T, though I'd encourage you, go to Wolfram Alpha, plot this thing as tanh of 1 over x. Okay, so it's as a function of temperature. And what you'll see is there's a suspiciously flat-looking patch here. And that's because this function sort of approaches, this asymptote, we approach exponentially, right? So tanh, again, it's sinh over cosh. As beta gets big, or as t gets small, right? The exponential parts are going to dominate. And so the difference between tanh and 1 is going to scale like e to the minus beta as beta gets large, or e to the minus 1 over t as t gets small. So at some point, it's extremely close to that asymptote and stays extremely close. Like you can't see that this is not flat, even when it's plotted properly, not just in my questionable drawing skills. So while there isn't a phase transition, if you just sort of glance at this plot, you say, wow, that comes to a sudden halt here. So this is one of these things where it's good to have an analytic result rather than just a numerical result. If you had just numerically done this, you might see this and think, wow, it's really flat and it looks like there's a corner. Secretly, there's not. Okay, so that's the exact solution for the 1D model. In the next section, we'll take a look at a way to approximate the Ising model in any dimension. Our second technique here will have a name that may sound familiar because we talked about this earlier with Bose-Einstein condensates, and that's the mean field approximation. If you remember from Bose-Einstein condensates, mean field means we're going to assume that every particle looks like the average particle. And then we can sort of self-consistently find the effective interactions by saying, well, the particle has to have this value, some value, and if every particle has that value, we can plug that into our energy and calculate the energy. And now we've got the value. So in the case of the BEC, the value was the BEC wave function, right? So we ended up with the BEC wave function in multiple places, which meant we had an equation we could solve for this mean field wave function. Okay. Here, spins can only have either spin up or spin down, right? Or we could talk about the average of that spin's orientation. Okay. So instead of a whole mean field wave function, which is a pretty complicated object, we're going to have a mean field average spin. Okay. So that's the idea. We're going to look at one particular spin, think about how it connects to every other spin in the system, and then at the end we're going to say, aha, let's assume that the average of these equals the average of this. This gives us a self-consistent equation that we can solve to get the average spin of any spin in the system, or equivalently, the magnetization of the system. Okay. Now, again, this is an approximation because in real thermal systems, a spin doesn't just take on its average value, right? This spin has to be either up or down anytime we look at it. But the average spin could be like 0.2, okay? So we'll never measure this thing as 0.2. It must be fluctuating thermally and just spends a little bit more time spin up than spin down, and that's how we get an average of 0.2. Okay? By ignoring those fluctuations, we're ignoring an important part of the physics, right? These two may happen to fluctuate together and then fluctuate down together, right? So this will always be negative epsilon, but it could average out to an average spin of 0, you see. So this is how you miss something. That's why this is an approximation. This is not exact at all. And fluctuations can be extremely important to these physical systems. And at the end of this section, we'll talk about one particular case where fluctuations are extremely important. And then you'll look at that case in more depth on the homework. So that's a place where this mean field approximation is going to break down. But as we go to higher and higher dimensions, it'll be a better and better approximation. We'll talk about why in just a second. Okay, so hopefully that sets the stage a bit. Now let's do it. Let's go through that operation. We're going to look at this spin. I've drawn this as a 2D system, but it doesn't really matter what dimension. We're going to wrap that up in this number n down here. So we'll look at this one spin. It's got some neighbors. The energy of that one spin is minus epsilon times the sum over its neighbors of its neighbor's spin dotted with itself. And itself doesn't change from neighbor to neighbor, right? So we can just write this as minus epsilon, the sum over all the neighbors dotted with spin number 1. So if this is spin up, then S1 is positive 1. So we just get minus epsilon times the sum over neighbors of the neighbor's spins. Or I could say the total spin of all neighbors. Equally good way to say it. And then if it's spin down, S1 will be negative 1. That cancels the minus out front. And we get positive epsilon times the total spin of all the neighbors. Okay. And when I add up the spins of all the neighbors, if I divide it by the number of neighbors, then I would get S bar, right? I'd get the average spin over all the neighbors. But I'm not going to divide by the number of neighbors. I just want the sum. So I've got S bar times this little n, which is the number of neighbors. Okay. This is what's going to change as we change dimension. If we have a 1D Ising lattice, so an Ising chain, n is equal to 2, right? Each particle has a neighbor to the left and a neighbor to the right. Now you might say, hey, wait a second, the first one and the last one don't have 2 neighbors. That's true. But we're thinking in large n, and so the average number is going to be extremely close to 2. We'll call it 2. Okay. The 2 edges should not have a substantial effect if we're working at large n. Okay. If we go to 2 dimensions, right, you can have up, down, left, right. So you've got 4 neighbors, n equals 4. 3 dimensions, you can do up, down, left, right. Sorry, that was my left, not yours. Except I think the camera reverses things. Anyway, you know what I mean. Up, down, left, right, forward, and backward. So we've got 6 neighbors. And just in a hypercubic lattice, you have 2 times the dimension number of neighbors. Okay, so we can find n for any dimension, but we'll just leave it there as a variable. Leaving it there as a variable means we're in principle doing the calculation for any dimensionality, which is nice. That's pretty powerful. So for that one spin, we can calculate its partition function. This partition function for the one spin, right? And it's just e to the minus epsilon s bar n plus e to the plus epsilon s bar n. Right? I said it backwards to how I wrote it. That's fine. E to the beta epsilon s bar n plus e to the minus beta epsilon s bar n. Did I say it backwards? I said it with the wrong sign. Okay, you know what I mean. I'm going to take the energy, I multiply it by minus beta. That becomes my exponent here. So if it were spin up, it would be e to the minus beta times minus epsilon, e to the beta epsilon s bar n. If it's spin down, it would be minus beta epsilon s bar n. And again, okay, we're getting, hopefully getting the hang of this now. This is just a hyperbolic cosine. So it's 2 cosh beta epsilon s bar n. Okay, it's getting to be a mouthful. There's a lot of stuff in the argument, but you know what all of these pieces mean. It's 1 over kT. This is the energy of interaction between 2 neighboring spins. This is the average spin of our neighbors. And this is our number of neighbors. Okay, so these combined gives us the total spin of the neighbors. Okay, good. So we've got the partition function. Again, we can start calculating other things. One thing would be, what's the average of S1? Okay. So, and I should say, so far we haven't actually made any approximations, but we can't do anything with this because we don't know what S bar is. So this is, we're moving to make the mean field approximation now. Since S bar is the one thing we don't know, we'll calculate the average value for S1, and then our move at the end will be to say, hey, average of S1, probably average of its neighbors. That's the approximation. Okay, so how do we calculate the average of S1? We just take 1 over the partition function times the spin times its Boltzmann factor, summed over all the different spins. Well, we've only got 2 spin orientations. It could be spin up, okay, S is positive. That's our case where our Boltzmann factor is e to the beta epsilon s bar n. Okay. And it could be spin down, which is to say S is minus 1. So minus 1 times a Boltzmann factor, which now is e to the minus beta epsilon s bar n. Okay. Again, should look familiar. It's this with a minus sign, which means it's a sinh. 2 times sinh. So 2 sinh beta epsilon s bar n. 1 over z is going to give you 2 cosh beta epsilon s bar n. And so once again, tanh makes an appearance. Okay, sort of you're seeing these hyperbolic functions seem to be key to understanding the Ising model. So now we still have what is an exact, if not particularly useful, statement, which is S1 bar equals tanh beta epsilon s bar n. But this s bar, the average of the neighbors, could in principle be different for every single spin that we look at. Now we make the mean field approximation, okay? So here's our equation, S1 bar equals tanh beta epsilon s bar n. We're gonna assume that all spins are the same, which is to say the average of spin 1 is equal to the average of its neighbors, okay? removing any possibility for fluctuations. And fluctuations give you correlations, so this also amounts to assuming they're all independent and they all take their average value. So this pays off by just changing this to S bar. So now we have S bar equals tanh beta epsilon S bar n. Okay. This is now an equation we can solve, right? It's a single equation with a single unknown, S bar. But it's a transcendental equation, so you can't just say, oh, here's the root, it's 5. Right? So what we're going to do instead is something that you may have done when you had similar type problems in quantum mechanics. I think it's the finite square well in 1D. You get like x equals tangent of x instead of tanh x. Okay, so similar idea. We can't solve it in closed form, but what we can do is plot the two sides where they intersect. That's a solution, right? So for beta epsilon n less than 1, okay, which is to say if I multiply both sides by kt, kt is bigger than epsilon n, so we're in some sort of high temperature limit, right? Our energy available through the heat bath, or our energy that connects with temperature, this is bigger than the interaction energy scale for my spin with all of its neighbors. So if we do that, that means that all this stuff is less than 1. That means the slope inside of this tanh is less than 1 as a function of S bar. So if we plot our functions versus S bar, the tanh has a slope less than 1 at the origin, while S bar has a slope of 1 everywhere, right? It's just S bar equals S bar. Or sorry, f of S bar equals S bar. So we've got a straight line with slope 1 for the left side. We've got this gently sloping tanh on the right side. They only intersect at one point, which is the origin. So in this high temperature regime, we don't have any average spin. The average spin is 0, or said differently, the magnetization is 0. Okay. Now, something that Schroeder mentions but doesn't really explain well, and I don't know that you would have seen this in your classical mechanics courses thus far. When we have an intersection here, that's a solution, which means this is one of the, it's one of the solutions to this equation, so it should be one of the possible states of the system. In this case, it's the only possible state. So the next thing I'm going to tell you is important. It's the one possible state of the system, but also we want to ask, remember in statistical mechanics, we're always looking at equilibrium. So saying this is a solution means it's a valid equilibrium point. We haven't really talked about being away from equilibrium at all because, well, that's harder. Okay. But one thing we can say is this equilibrium stable? Now, how would we know that? So what we would say is, suppose we fluctuate away from 0. Okay? The mean field approximation has ignored fluctuations, but let's say something has fluctuated our magnetization away from 0. We've got a small negative magnetization here. Okay. Well, we have tanh equals S bar. So this should come over to here. Okay, so we're going to take our value of tanh, come over to the S bar curve, right, which is just a straight line. Say, no, this is our new magnetization. But if S bar is our new magnetization, it should also be tanh of this stuff, right? So from here we say S bar equals this new value, plug it into the tanh. That gives us a new value for S bar. If that's our new value for S bar, we should plug that into the tanh, right? We're just iterating this, saying, it fluctuated away, but in the next moment it's going to update to this value. And if it's updated to this value, then we should take tanh of that stuff, right? So going over here means we're taking this thing, making it our new S bar. Going back up to the tanh curve means we're plugging our new S bar into here to get a new value, right? So we're updating our S bar. this is certainly not exactly what happens physically, but this is sort of a proxy for the time evolution of the system away from equilibrium. And what you see is that when we went to some negative magnetization or negative S bar, this thing is walking back up towards 0. Similarly, if I go positive, right, I'll come over to S, down to tanh, over to S, down to tanh, over to S. So this is also going to 0. So if I fluctuate away from 0 in either direction, the dynamics is going to drive me back towards 0. That means this is a stable equilibrium point. So at high temperature, S bar equals 0 is a stable equilibrium. Now, if that was the whole story, we wouldn't really have to talk about that, right? It's the only equilibrium. But when we go to beta epsilon n greater than 1, or kT less than epsilon n, so this is some low temperature regime, beta epsilon n greater than 1 means that the slope of this tanh at 0 is greater than 1. Okay? So if we draw S bar as this blue line again, when we go through the origin, right, tanh needs to be steeper than that. Okay, fine, we'll draw it steeper than that. The problem is we also know tanh has to asymptote to 1 and minus 1, which means it's going to have to cross S bar again, once positive and once negative. So now we're looking at a situation where we have 3 equilibrium points. And the question now is important. Which ones are stable, which ones are unstable? You can just sort of verify for yourself. I've drawn it in. If I'm at 0 and I fluctuate away to a positive value, I follow over to S bar, up to tanh, over to S bar, up to tanh, over to S bar. I'm walking toward this other equilibrium point. Similarly, if I start from this equilibrium point, well, clearly if I go down, I'll get pushed back because we just did that part. Right? If I go up, then I go over to S bar, down to tanh, over to S bar, down to tanh. Right? So this is a stable equilibrium. And I haven't drawn it in, but I hope you can see that there's a symmetry here. And so if you do the analysis, right, you're going to go up to tanh, over to S bar, up to tanh, over to S bar. This is also a stable equilibrium. So for kT below epsilon n, we now have 3 equilibrium points, 2 of which are stable, 1 of which is unstable, and the 2 stable ones have non-zero magnetization, or non-zero S bar. So in fact, when kT equals epsilon n, this is the point of a phase transition. This is where the tanh would have a slope of exactly 1 here. So the tanh would stay very close to S bar for a while before finally rolling off to its asymptote. Okay. That point where the phase transition is, you've seen this notation Tc before, that temperature is the critical temperature for this phase transition. So if we go any lower than that, it won't just follow S bar for a while before it curves away, right? It will be bigger in slope, and so it has to cross S bar 3 times. So that prediction from mean field theory would say that in any dimension, right, because all that the dimension does is change n when we're doing the mean field approximation, for any dimension, we will have a phase transition. And the critical temperature will just be lower as we go to lower dimensions because n gets smaller. What we already learned, though, is that the one-dimensional Ising model does not have a phase transition. It magnetizes, but it magnetizes continuously as you go to 0 temperature. So the mean field approximation is wrong. Well, it's an approximation. We shouldn't be terribly surprised that it's wrong. However, as you go to higher and higher dimensions, the mean field approximation gets better. So again, I mentioned in 2D, you actually can do a complete solution of the Ising model. The 2D Ising model does have a phase transition. This doesn't get the critical temperature quite right, but gets you in the right ballpark. So as you go to higher dimensions, the mean field approximation gets better. And why is that? Because in higher dimensions, you have more neighbors, right? As you have more neighbors, the idea that the average for your spin is equal to the average of the neighbors, that becomes more accurate, right? So we're ignoring fluctuations in the average of the neighbors, but if there are a lot of neighbors to average over, then the fluctuations will be a smaller fraction of that average. Okay? So this is, in the same vein as things we talked about right at the beginning of the course, where we said if we've got a large number n, we can find the average of some quantity, and the fluctuations away from it will look like 1 over root n times the average. Okay, so here we're taking the average spin of all the neighbors, and those fluctuations are going to look like 1 over the square root of n. Well, in 1D, 1 over the square root of 2 is 0.7, as your fluctuations are as big as your average almost. Okay? Go to 2D, it's a half. 3D, it's 1 over 2 root 2, so 0.35, 0.36, almost a third, right? So the fluctuations are getting smaller as you go to higher dimensions, which means the mean field approximation gets better and better. Okay. Last point I want to make, at this critical temperature, I said now more than once, tanh will have a slope of 1 at 0. 0 is still the only equilibrium point, and it is technically stable, but it's sort of very weakly stable, right? These two guys have the same slope at the origin, which means if we get just a little bit away from the origin, yes, I'll still do this over to s down to tanh, over to s down to tanh, but since their slopes are so similar, I'm making very small steps. In other words, at the critical temperature, while zero magnetization is in some sense stable, fluctuations away from zero are very, very slow to damp back to zero. So at the critical temperature, fluctuations become very large. There's sort of nothing stopping them from getting very large. Because, again, this is sort of very mathematical, but because S bar and tanh, beta epsilon and S bar, look almost identical at zero. So that means that you'll have large fluctuations, and those large fluctuations are exactly the sort of thing that we expect mean field theory to be bad at. Okay. Some of the payoff from that will be in the problem set. You'll be calculating things at the critical temperature, things called critical exponents, which will be explained in the problem. And when you do those calculations of mean field theory, they won't give you the correct numbers. However, the story is the same again, that as you go to bigger and bigger dimensions, those numbers get better and better.